Hello, welcome to this video where I'm going to go through chapter 11, a bunch of logs and exponents. So what we'll do is practice some expressing logarithmic expressions as a single log. Expanding logs, we'll be solving some logarithmic equations, solving exponential equations, simplifying a bunch of exponential expressions, converting between radical and exponential form, and then we'll take a look at some applications of exponential equations, which we'll be solving with logarithms. So good amount of stuff. So we'll start with just some of the basic writing as a single log. So I have two log expressions here that have the same base number of 5. What I'm going to do first is apply one of my log properties that says what I can do is take this 3 and bring it up as an exponent to my variable p. So I'm going to write it like this. And then my next step, because I have a plus sign here and because my logs have the same base number, what I'm allowed to do is write this as a single log as a product then of these two values. So log base 5 of np to the third. And sometimes you'll see me write this in parentheses. It means the exact same thing. The next one, same type of process, except this one is with natural log, which I'm still able to apply these rules. The first thing I'm going to do is bring this down as the natural log of 2 plus the natural log of r to the 1/3 power minus the natural log of the letter s. So what I'm going to do is also simplify that second expression and write that as the cubed root of r. So since 3 is my denominator, that would become the index of my radical. And then I can bring down the rest of my expression. And then the last thing I can do is apply that property that I had done here, where if I have an addition, it's going to be the product of these two values, and then my subtraction is going to turn into a quotient. So I'm going to rewrite this as the natural log of 2 times the cubed root of r over s. And again, I could throw that all in parentheses, means the same thing. It's divided by s because of subtraction, so that's what turns it into a quotient. So now I'm going to do that same process but backwards. So I'm going to expand these as separate logs. So I have a base number of 4 and I have two values here. So I'm going to be splitting this into two separate logs, both with a base of 4. So I'm going to first write it as log base 4 of the square root of x. And then since it's a division, I'm going to bring a minus down and write it as log base 4 of y. And then what I'm going to do is rewrite this as an exponential expression. So I'm going to convert this into exponential form by writing x to the 1/2 power. Since this is square root, my index value would be 2, and that would become my denominator of that fraction. And then I can bring down the rest of my expression. And now I'll take the final step of writing this as, my last step is bringing the exponent down then is a coefficient to the logarithmic expression. So 1/2 log base 4 of x minus log base 4 of y. And the last one of these, I'm going to break this up into two logarithmic expressions. The base number is 10. It's invisible, so if there's no base number written, it's implied that your base is 10. And I'm going to split this into two separate logs. So this is as easy as me saying log base 2 plus log of m. And sorry, log of 2 plus log of m. So the base, again, being 10 of both of these, it's a plus sign because these are being multiplied together. So what I'm going to do now is solve some log equations, and we'll have to do that same process of simplifying before we can solve in some of these. So what I'm going to do in this first case is rewrite this as 3 to the power of 4. So what I'm going to do is convert this from logarithmic form into exponential form. So I'm going to write it as 21x minus 3 equals 3 to the 4th power. And now I'm going to simplify. So I'm going to write it as 21x minus 3 equals 3 to the power of 4, which is 81. And I'm going to add 3 to both sides. And 21x is equal to 84. So now I can divide both sides by 21, and x comes out to 4. So if I wanted to check this answer, all that I'd have to do is substitute my value of 4 in for x, and your calculator could actually simplify this or evaluate that entire expression for you, which I'll do a walkthrough of that. Oops. So what I'm going to do is, in the calculator, you'll need a newer operating system for this. If I press alpha, and then zoom, alpha and then window, I can go down to the option that says log base, and I'm going to select that. My log base is 3, and then I'm going to write 21 times my value of x, which was 4, and then the minus 3. So this would appear to be the left side of my equation. If I hit enter, I should see 4, and I do, and that tells me that my answer is right. The next one, what we're going to have to do is simplify this as a single log first. Notice I have the minus sign, so that implies that I'm going to be dividing these two values. So I'm going to write this as a single log is log base 2 of 4x plus 4 over 3, and that is equal to 4. So what I'm going to do next is convert this into exponential form. So I'm going to leave my left side as 4x plus 4 over 3, and my right side base number is going to be 2, and I'll be raising that to the 4th power. So I'm going to scroll down a little bit. This is going to turn into 4x plus 4 over 3 equals 16. So 2 times 2 times 2 times 2. I'm going to now multiply both sides by 3. So that's going to get rid of the 3 in the denominator here if I do it on the other side. So I'll be left with 4x plus 4 equals 16 times 3, which is 48. And then solving from here, I'll subtract 4 on both sides, and that's going to give me 4x equals 44. Divide by 4, and x equals 11. So again, if you wanted to substitute that back up into the top expression, you could, and it would work out. The last problem, I'm going to make a small change, otherwise we're going to have a ridiculously large number here. I'm going to make a change to this problem, and I'm going to change this value to 3. It's still going to have a large answer, but I think it's going to be a little bit smaller than what it should. Well, actually, it's going to be a crazy amount smaller than what it would have been. And I'll show you why that is. So this is a natural log problem. The first thing I want to do is isolate that expression by adding my 2 to both sides of this. So what I really have is the natural log of x minus 3 equals 3 plus 2, which is 5. Now this is why I changed the problem. The next step is to take the inverse of a natural log, which is e. And when I take e to this 5th power, it's going to give me a large number. If that large number would have been my original value of like 48, I would have ended up taking e to the 50th power, and that would be a ridiculously large number. So my e and my natural log are inverses, so those will cancel each other out. I'll be left with my expression of x minus 3, and then in my calculator, I'm going to press second and then ln, and what that's going to do is bring my my e value in. And e to the 5th is 148.413. And then all I'm going to do is add the 3 to both sides. So I'm going to end up with 151.413. And just to show you how I can check my answer then, I'm going to evaluate the left side of this expression. So I'm going to clear out my calculator, and I'm going to type the natural log of my answer, which was 151.413, and then the minus 3, and I'm going to close the parenthesis and put minus 2. And that's going to evaluate this entire left side. So I should end up with something pretty darn close to 3. And there it is, 2.9 repeating. And again, the only reason why it doesn't tell me that that's 3 is because I chopped off this decimal before. So we are correct on those. Move on to the inverse of that, which would be solving exponential equations. And we'll round to the nearest thousandth, so 3 decimals out. So the first thing I'm going to do is apply a property. Well, I can actually log both sides first, and then I'll apply an exponential property. So I'm going to evaluate a log on the left and a log on the right. So that's the first thing I can do. And now I'm going to take this 2 minus x, and I'm going to bring it down as a coefficient to the log. So I'm going to write this as 2 minus x log 2 equals log 15. And then I can divide both sides by log 2. And that's where I'm going to go to the calculator then, and we're going to press log 15. Keep in mind I got to close the parentheses, divided by log 2. And that's going to give me 3.907. So that's the right hand side of my equation, and then the left side I had 2 minus x. So a couple ways we can kind of go about solving this. First thing I'm going to do actually is just subtract the 2 on both sides. So I'll have negative x equals, and if I subtract 2 here, and I'm going to subtract 2 here, I'm going to get 1.907. And then my last step would be to divide both sides by -1. So I'll end up with x equals -1.907. Alright, let me go back up. The next one has e, and my inverse of that's going to be natural log, so I'll eventually use that. My first step is to subtract 30 on both sides to isolate that expression. 2 minus 30 is -28, and that's equal to -e to the 2x. Now, because my calculator cannot do negative natural logs or negative e's, what I'm going to do is divide both sides by -1. And that's going to turn this into a positive 28 equals e to the positive 2x. And now I can apply my inverse function, which is natural log. So I'm going to say natural log 28 equals the natural log of e to the 2x. That'll cancel out. Natural log of 28 can go in my calculator. So I'm going to put in natural log of 28, and that's going to give me 3.332, and that's equal to 2x. So then my last step would be to divide both sides by 2. And go right back up to this, hit divided by 2, and I'll end up with 1.666. Alright, and then lastly, I have a problem where I have exponential expressions on both sides with my variable in the exponent. So what I'm going to first do is log both sides of this. Oops, let me switch color. I'm going to log 4 to the 2 plus x equals log of 2 to the x plus 1. And next I'll apply that property where I'm going to bring the 2 plus x down as a coefficient to log 4. And I'm going to bring the x plus 1 down in front of the log 2. So what I'm going to do next is divide both sides by log 2. And that's going to get rid of this value. And I'm going to go into the calculator and type this part in. So I'm going to end up with 2 plus x. And then here's where I'm going to throw that log 4 divided by log 2 in my calculator. And that's going to give me a value of 2. And sometimes you're going to get a really ugly decimal for this value, whatever that comes out to. You would just round to the nearest thousandth then. And that's equal to x plus 1. So the next step then, and like I said, this is not always going to come out to be a pretty value like 2. Sometimes you'll get a decimal. You'll still solve the same exact way. I'm going to distribute the 2 across and have 4 plus 2x equals x plus 1. And then I'm going to subtract 1 on both sides and get 3 equals 2, and that's going to be 3 plus 2x equals x. I'm going to subtract 2x on both sides and get 3 equals negative x. And then if I divide by -1, x is going to come out to -3. And then once again, to check your answer really quick, you would just substitute that value back in to the exponent spots in both of these values of x, and your answer would check out. Alright, just some simplifying. So I'm going to simplify each of these expressions using some rules of exponents. First, I'm taking a product of these two values, which is -8. And now, if I have common base numbers, in this case I have both x's here, what I can do is add my exponents. So x to the power of 4 plus 5, which is -1. And then y to the power of the 6 plus this 1, which is 7. And lastly, because I don't want negative exponents in my answers, I can keep the -8 and the y to the 7th on my numerator, and I can drop the x to the negative first on my denominator and make the power positive. And because I brought it down to the denominator, that's what changes it from the negative to positive, and that would be your final answer for that problem. With this one, very similar to how I took a product of these two values, I can divide or just simplify the 3 over 15, and I'm going to simplify that as 1 over 5. And now, because in this problem was a product, I added my exponents. This one's a quotient. I'm going to subtract my exponents. So I'm going to end up with m to the 10 minus 5, which is 5, and n to the 8 minus 2, which is 6. So you don't even need the 1 here. I could just leave my answer as m to the 5th, n to the 6th, all over 5. Alright, a couple of these problems where I'm going to convert these from radical to exponential form and vice versa. With this first one, your index value is the outside of the radical. That's going to become the denominator when I write these in exponential form. And you're just going to break it apart and say this is x to the power of 3 over 5. So your exponent stays the same here as a numerator. And then y to the power of 10 over 5, which I'm just going to express that in a simplified form. So I'll leave it as x to the 3/5 and then y to the 10 over 5, which is 2. And that's as far as you really need to go with a problem like that. We're just converting it from one form into another. I'll do the same thing here, but in a different direction. So I want to write this in radical form. So my index value of my radical is going to be the denominator of these fractions. So the first step I'm going to do here is find a common denominator. So my common denominator between my 3 and my 2 is going to be 6. 3 would need to be multiplied by 2 to get to 6, so I'm going to do the same for my numerator. And then 2 would need to be multiplied by 3, so I'll do the same to my numerator. Now that I have a common denominator here, that's going to become the index value of my radical expression, and then the numerator values would become your powers. So m would be squared and n would be raised to the 9th. Alright, last problem then, or problems, what we're going to do is evaluate a few exponential equations for an investment at a certain interest rate. So this says write and evaluate 3 exponential equations for a $5,000 investment at 3.92%. And there's these 3 different accounts. So semi-annual means I'm going to be compounding twice a year. Monthly means we'll be compounding 12 times a year. And continuous compound means I'm going to use the letter E as my base number. And then my time value will be a period of 30 years. And we're going to round to the nearest whole dollar. So we'll evaluate these 3 expressions. So I'll put a couple equations up here. For the first 2 equations, we're going to use a function a of t equals p0 or p0, which stands for your principal amount, and then 1 plus the interest rate as a decimal over the number of times it's compounded to the power of that number of times that it's compounded times t. So we'll be using this formula for the top 2, and then for the continuous one, I'm going to use a sub t equals p times e to the rt. So because it's continuously being compounded, we can use the letter e as the base number of that expression. So I'm going to write my 2 equations first. A of t equals, my original amount was 5,000, and I'm going to use 1 plus my interest rate, 0.0392. It's semi-annual, so that means it's compounded twice in a year, to the power of 2t. And then I'll do the same thing for this one. I'll do a of t equals 5,000. And this one's monthly, so the only change that we're going to see here is that my denominator is going to be 12 now. And then same thing for my power. I would write 12t. So this is compounded every month. That's a really ugly t. I'm going to rewrite that. And then last one, the continuous, is going to be a of t equals, you're starting with that 5,000, times e, and same interest rate, 0.0392 t. So what I'm going to do is evaluate these 3 expressions now for a value of 30. So a of 30, and I'm going to go to the calculator then, and what I'm really doing is substituting 30 in for these t values. So I'll show you the first one, and if you have the newer operating system on a calculator, this will look really smooth, just like this fraction here will. So I'm going to type in 5,000 parenthesis 1 plus, and now this is what I'm talking about. You're going to press alpha and then y equals. And the first option, n over d, stands for numerator over denominator. And it's pretty slick. You'll put in 0.0392 over my denominator, which is 2. And then I'm going to hit the right arrow, close the parenthesis, and raise this to the power of 2 times by 30. So the time value of 30. If you have an older operating system, you won't be able to do a little fraction trick. What you would instead do is put this fraction in parentheses, and the exponent would also go in parentheses. So I'm going to evaluate that, and it's $16,024 if I round up. And I'll do the same thing for my next one. So the monthly one, 5,000, parenthesis, 1 plus, alpha, y equals, there's my fraction, 0.0392. And this one was compounded monthly, so it was 12 times in a year to the power of 12 times 30. And that one is going to come out to 16,176. So it's a little bit more. And then the last one, we're going to be using E for this. So I'm going to type in 5,000 and then press second and then the ln. And there's my E, and 0.0392 times 30. And that one is 16,207. So real quick, I'm going to look at the difference between these amounts. And what you would see is I'm compounding more as I work my way down. So this one was compounded twice a year. This is 12 times in a year. And continuous means it's always adding on interest. So you can see that the dollar amount would be more for the more that it's compounded. So what that's doing is it's adding on interest more and more and more. And then it's making that amount higher, and then it's taking a percentage of that amount, and it keeps adding on a greater amount. And that's why that amount comes out higher. And then lastly, how long will it take the continuous compound account to double? So I'm going to bring that function down here. A of t equals 5,000 times e to the 0.0392 t. And I'm keeping the t up here. I'm not putting 30 in because we're going to solve to see how long it'll take for it to double. So when this account doubles, it'll be worth $10,000, and that'd be my final amount. So I'm substituting that in for the left side of the equation. And what we want to do, is solve this. So the first thing I'll do is divide both sides by 5,000. And I'm going to end up with 2 equals e to the 0.0392 t. And now I'm going to take the natural log of both sides. So the natural log of 2 equals the natural log of e to the 0.0392 t. And that's going to cross that off. So I'm going to go to the calculator and type in the natural log of 2 and get 0.693. And I'm going to set that equal to 0.0392 t. And then I can divide both sides by 0.0392, and that's going to end up giving me the time that it takes measured in years. Why did I put a t next to that? The t is going to be by itself, and that t value, so divided by 0.0392, that t value represents the time that it's going to take for this account to double. So between 17 and 18 years. So I'll put 17.68. which means it'll take between 17 and 18 years for that account to double. So quickly recapping a lot of what we had done. So we started by simplifying some logarithmic equations by expanding or condensing them. We use that information to solve log equations and exponential equations. And then we practiced a little bit of simplifying using some rules of exponents and some conversions between radical and exponential form. And then we applied a lot of the exponential and logarithmic equations into a money problem dealing with different types of interest.